Hi, in this video I want to talk about sensor fusion on high resolution data, specifically audio, and also touch upon processing multiple data from multiple microphones in a Impulse. So I'm doing it in the context of this EarNAS project. There's 3 sensors, 2 microphones, so 2 audio channels here, and then an accelerometer. I don't really know what they want to detect. I think first click, second click, and silence. I don't know what that means. Let's investigate. So if you want to process this in a studio, the kind of the default way would be to say, well, I'm going to create 3 DSP blocks. Spectrogram-based one for audio, spectrogram-based one for audio 1, and then a spectral analysis block. And it works, right? The big downside is that what you get out of this is essentially 2 spectrograms concatenated, and then some random features around spectral analysis. And so you're limited in the type of neural networks you can run over that. You can't really run a convolutional neural network over it, because you can sort of do this on the 2 microphones, right? Convolutional network. But then what are you going to do with the spectral analysis features? So the only thing you can really do is a fully connected network, which is not too great for audio data, because if you look at a pixel in a spectrogram, this pixel on its own doesn't really mean anything, right? That's why you typically do convolutions over the network. So what would be a better way? Now, essentially what we do in the DSP process is that we take raw data and we turn that into something smaller, right? So less features, and highlighting the stuff that we care about. So here, for example, we remove noise as well, and we highlight, certain frequencies. A DSP block, like signal processing, is not the only way of doing that. What powers the data explorer is a combination of these 2 things. So it's a combination of signal processing and then a neural network, not running the full neural network, but rather we cut it off somewhere near the end and we use those embeddings. Because if you think about a neural network, right, for audio processing, you pass raw audio in, then all kinds of like magic stuff happens here. And typically what kind of calculation are being made, that happens in the training process. And then finally you learn, was the silence 1 click or 2 clicks? So the interesting part is that we can cut this off here. And instead of having this classifier head, we just cut it off here. We then have features. These features have already removed this time component, right? Because there might be convolutions happening here. And those features are sort of learned DSP block. It's something that a neural network has learned. So that's really interesting. So I figured the approach that we want to take here is that rather than throwing a raw spectrogram into the classifier, we throw embeddings in. So we run basically 2 neural networks, one to create the embeddings and then one to find the learned classifier. And the beautiful part there is that we can do that with multiple neural networks, right? So we do 1 neural network for audio 0, create the embeddings, another neural network for audio 1, create the embeddings, and then we run a normal spectral analysis block. And those 3 things you can throw in a network and just run a fully connected network over it. That's in theory. So how would you create that? Let's first just train something on a single audio axis. So I create a spectrogram block, normal classifier, create my spectrogram block, and I train a normal classifier. Here a convolution, here a CNN. It's just the default stuff in Studio, just next finish. And we get something that actually separates nicely. So that's a really good sign. So this project, the only reason that I made this project is just to create those embeddings. So let's take a look at how it looks like. So let's go to dashboard, download the TF-Lite file. And let's take a look at that file. All right, so make this bigger. Yeah. So what we pass in is still the spectrogram. So the DSP stuff doesn't go away, right? We have spectrogram, 1950 features, we reshape, and then at the end we have these 3 classes, but we cut it off here. So we have 128 features coming out of this thing. And that's going to be the output of our DSP block. That's it. So So I put a little example script here in this repository, audio sensor fusion DSP block. So essentially what we do here is I have a little script that takes in a saved model. You can download that from the dashboard, and cuts off the last layer and writes out a TF-Lite file. And that TF-Lite file is here. So this is going to be the exact same thing as we had before, but now we end with 128 features, cutting off the last little softmax part. So in our DSP block then, so this is implemented as a custom DSP block, very simple. We do a fixed parameter spectrogram. And why does that need to be fixed? Well, because the input size to the neural network is fixed. So I hard-coded these variables here. So we first run our spectrogram code, the exact same stuff as we normally do in our DSP block, right? Stack frame calculation. And then finally, we're going to pass it through the neural network. So we have our features from the spectrogram block, and then we pass it to the neural network. So rather than raw spectrogram output, you now get 128 features out. That's it. So I run this as a custom DSP block, and that is in my project here. So I have 2 blocks for the audio embeddings, and those are my custom DSP blocks, and then 1 spectral analysis block. So if you look at the audio block, let's get a second click. We output still, we draw this little graph, but the processed features is 128 because those are the neural network features. All right, from there I can just train my network as usual. So I create the features on both sides, create the spectral features here. Pretty cool visualization, by the way. And finally, I train my classifier. So this all just works in Studio as everything else. So small network and really good accuracy. If you remember from the CNN on one channel, it was like 1% lower. Also really good accuracy on the test sets, 98.7%, not bad. Okay, so that's the part in Studio. I think that's pretty straightforward. How can I run this on device? So, as you might have seen in the video about custom on-device DSP, we have this ability to now host neural networks in our DSP blocks. Same thing as we're doing now. So what I say here in the get TF-Lite implementation is actually, hey, I'm using embeddings quantized.tflite as my TF-Lite file. So when we now export this DSP block, it will compile this DSP block through the Eon compiler, and this gives us this compute graph as well. I've already done that. So I have in my TF-Lite model, not just my neural network here, but I also have a DSP block that is compiled and another one. Actually, these are the exact same thing because it's the same neural network underneath. However, what is lacking here is the spectrogram part. So if you look at the output of this model once we export DSP blocks, you see that actually for this DSP block, we just call this neural network because that's the only thing we said that we're gonna run. So we want to get an implementation, on-device implementation that does 2 things. First, run the spectrogram, and then run the neural network part. And we can do that with a small bit of our own code. So let's copy this stuff in. Okay, so we can write a custom DSP block here. I'm going to call it spectrogram Eon features. First spectrogram, then Eon. Here I say extract TF-Lite features. No, I want to use spectrogram Eon features as my feature extractor. And then we can implement that ourselves. So I can say here, so this is a custom DSP block. The first thing that I do is I create hard-coded spectrogram config again. Then I create the features, same stuff. So take the signal, go through a spectrogram block, and then I have my features. And then we just call the neural network block. So to run the neural network, and we're done. That's how easy it is. And yeah, there's literally nothing more to it. So we use the EON compiler to just compile the neural network part for us, and then the second part is using our SDK to create the full block. Let's see if that actually works. So let's go find a sample. All right, let's get the raw features. So the output here should be second click. There we go. XMCP. Run it, build it. And there we go. Second click. Yeah, that's all there is to it. Using embeddings, especially if you kind of the new stuff that we do in DSP blocks, the compilation of neural networks make this really easy to use this kind of embeddings approach. Here, what is really cool here, you can use this with a pre-trained block or pre-trained neural network, like Sean's postnet indicator. You can use it with a DSP block that or a neural network that you've trained yourself, like we do here, or even do a combination of both DSP code and neural network to get even better features. And yeah, as I showed here, there's a small bit of work that you need to do on the embedded side, but it's easy. We have our whole SDK available. It mixes and matches really quickly, and with a couple of lines of code, you can do stuff like this. And now we do sensor fusion on 2 microphones and an accelerometer. It's pretty cool. All right, thank you, and I'll throw a link to the repository down below.